Imagine you're standing in front of two identical looking cars. Same size, same color, same shiny rims. One of them has a yellow sticker on the windshield that says diesel. The other has a similar sticker that says petrol. Now here's the $1,000,000 question. Why does one of them sound like it's trying to murder you every time it starts, while the other purrs like a kitten designed by accountants who've never heard the word excitement? Or wait, maybe I've got it backwards. Maybe the diesel is the quiet one, and the petrol car is the one that screams like a teenager who's just discovered heavy metal music. Welcome, friends, to one of the most confusing debates in automotive history. Today we're going to answer a question that has baffled humanity since the dawn of the internal combustion engine. Well, not quite the dawn exactly. The diesel engine came a bit later, but we'll get to that. I'm going to teach you everything you need to know about diesel and petrol engines. Not just the basics, but the really interesting stuff. The kind of facts that will make you the most fascinating person at your next dinner party. Assuming your dinner parties are attended by people who unironically say things like, "Oh, interesting, you know about compression ratios?" By the end of this video, you'll understand exactly what makes these engines different, where they came from, why we use both of them, and what the future holds. Plus, I'll throw in some jokes because apparently the algorithm rewards engagement, and my mortgage payments depends on you lovely people watching till the end. So let's begin, shall we? Well, first, if you're new here, welcome to What Is, the channel that answers the questions you never knew needed answered. We're like that friend who knows a little bit about everything and won't stop talking about it. Consider subscribing. It's free, unlike my student loans. Let's start off with the origins. Every great story has a beginning, and the story of the internal combustion engine begins in the most German way possible, with a man named Nicholas Otto. No, that's not a typo. This Nicholas, born in 1832 in Holzhausen, Germany, wasn't related to the Tesla fellow, despite what the confusion in your head might suggest. Otto was an engineer who in 1876 built the first practical four-stroke internal combustion engine. We call it the Otto cycle to this day, which sounds like either a roller coaster or a painful medical procedure, depending on your perspective. Now here's where it gets interesting. Otto's engine ran on something called town gas, which is exactly what it sounds like. Gas made from coal that cities would produce and distribute like, well, city gas. It wasn't very efficient and it wasn't very portable, but it worked. Sort of. Like a car that only breaks down 3 times before making it to the store. Then came Gottlieb Daimler and Carl Benz. Yes, that Benz. The one with the fancy car brand. These two geniuses figured out how to make petrol, which is just gasoline refined from petroleum, actually run an engine properly. By 1886, Benz had patented the first true automobile, and Daimler had created the first four-wheeled vehicle powered by a high-speed petrol engine. Meanwhile, across the channel in England, a clerk named Frederick Winslow Diesel was having what I can only assume was a series of very stressed thoughts about efficiency. Diesel was born in Paris in 1858 to German parents, and he was obsessed, and I mean obsessed, with the idea of creating an engine that could compete with steam power without all the hassle of boiling water and waiting around. Steam engines, you see, were wonderfully efficient in theory, but absolutely terrible in practice. They required huge boilers, lots of fuel, lots of water, and lots of patience. Diesel's breakthrough came from a deceptively simple question. What if we didn't need spark plugs at all? In 1892, Diesel filed his patent for a rotational heat motor that worked by compressing air so tightly that it got hot, really hot, and then when fuel was introduced to this superheated air, it would ignite on contact. No spark needed, just compression, heat, and boom. Well, not boom exactly. That's the petrol engine's speciality. More of a controlled whoosh. The first practical diesel engines were massive things. Too big for cars, mostly used in factories and ships. It wasn't until 1936, nearly 40 years after diesel's patent, that Mercedes-Benz built the first diesel-powered passenger car, the 260D. And even then, diesel cars remained a niche market, popular mainly among taxi drivers who appreciated the fuel economy, and people who wanted their neighbors to know exactly when they were leaving for work. But what about petrol engines? Well, they had nearly a 50-year head start. By the time diesel cars were becoming practical, petrol engines had already conquered the world. Henry Ford's Model T, introduced in 1908, ran on petrol, and became the first automobile that normal people could actually afford. The combination of petrol's energy density, the relative simplicity of spark ignition, and Ford's manufacturing genius created a perfect storm that made petrol the obvious choice for personal transportation. For nearly a century, petrol reigned supreme. Diesel lingered in the shadows. Trucks, trains, ships, and the occasional eccentric millionaire's luxury car. They coexisted like two species in the same ecosystem, each occupying its own niche, neither really competing with each other. But why? What makes them so different? That's what we're going to explore next, and believe me, the differences are fascinating. The key differences. Alright, pay attention, because this is the good stuff. The stuff that separates people who understand engines from people who just put gas in them and hope for the best. The fundamental difference between diesel and petrol engines comes down to three words: compression, ignition, and explosion. Yeah, well, that's actually 4 words if you count the ands separately, but let's not get pedantic. Let's start with the petrol engines because they're actually more complicated in a counterintuitive way. A petrol engine works by drawing in a mixture of air and fuel, compressing it to about 1/10 its original volume. Compression ratios typically range from 8:1 to 12:1, and then, right at the peak of compression, a spark plug fires. That spark ignites the mixture, creating a controlled explosion that pushes the piston down, converting chemical energy into mechanical energy. It's elegant in a way, a tiny controlled explosion, perfectly timed, happening hundreds of times a minute. The engine's computer, or in older cars, a distributor, decides exactly when to fire the spark and get the best power and efficiency. It's like conducting an orchestra, where every instrument is a tiny controlled explosion, and the conductor is a computer that can make decisions in milliseconds. Diesel engines, on the other hand, don't mess around with spark plugs. Zero, zip, nothing. The diesel approach is pure, brutal efficiency. Air is drawn into the cylinder and compressed to a much higher ratio, typically between 14:1 and 25:1. Sometimes even higher. This extreme compression heats the air to a temperature around 1000 degrees Fahrenheit, which is roughly the temperature of a pizza oven, and significantly hotter than you want your car engine to be under normal circumstances. At the precise moment when the air is superheated, fuel is injected directly into the cylinder. Because the air is so hot, the fuel ignites immediately upon contact. No spark needed. No carefully timed electrical discharge, just compression, heat, and pure chemistry of diesel fuel meeting superheated air. This is why diesel engines are so robust. There are no spark plugs to gap, no ignition coils to fail, no distributors to wear out. The fuel system does all the work. And if you've ever priced a diesel fuel injection system, you can confirm that all the work comes with an appropriately large price tag. Now here's where things get really interesting, and where most people get confused. Petrol engines are designed to prevent unexpected ignition. The fuel-air mixture in a petrol engine is carefully calibrated to burn cleanly and predictably when sparked, but not to ignite spontaneously from heat and pressure. If petrol auto-ignited from compression alone, the engine wouldn't work properly. You'd have random explosions happening in the wrong times, which is bad for longevity, and also not exploding. Diesel fuel, by contrast, wants to ignite. It's specifically formulated to have high auto-ignition temperature in the context of a controlled ignition, meaning it waits patiently in the fuel line until it's injected into the superheated air, at which point it enthusiastically combusts. The cetane rating of diesel measures how quickly it ignites, like an octane rating, but for diesel, and in the opposite direction. High cetane means quick ignition, which is desirable. But wait, there's more. And by more, I mean the elephant in the room, that everyone notices but nobody can quite articulate. The sound. Diesel engines are loud. There's no diplomatic way to say this. From the moment you start a diesel engine, it announces its presence to the entire neighborhood. Like that neighbor who plays the acoustic guitar at 7 a.m. Why are you doing that? It comes down to the rate of combustion. In a petrol engine, the spark ignites the mixture, and the flame front spreads relatively slowly across the combustion chamber. It's a gentle, controlled burn. In a diesel engine, when fuel is injected into the superheated air, it ignites everywhere at once. The injection process itself creates a bit of a shockwave. The combustion happens faster and more violently. This rapid pressure rise creates that characteristic diesel clatter, especially at idle. Modern diesel engines have gotten much quieter through careful engineering, better fuel injection systems, sound dampening materials, and refined combustion chamber designs. But they'll never be as quiet as petrol engines. It's physics. You can't change the laws of physics. You can't fight physics and win. Unless you're building a Formula 1 engine, in which case you're fighting physics and everyone's impressed. Another key difference involves weight and power density. Diesel engines are typically heavier than petrol engines of equivalent power because they need thicker walls to handle the higher compression ratios and the resulting pressures. This makes diesel engines great for applications where durability matters more than weight, like ships, trucks, and heavy machinery, and less ideal for applications where every pound matters, like sports cars and aircraft. Petrol engines with their lower compression ratios and spark ignition systems can be built lighter and rev higher. That's why your average sports car engine revs to 7,000 or 8,000 RPM, while most diesel engines are lucky to see 4,500. It's not that diesel engines can't rev high, it's that the design constraints make it impractical and expensive. Fuel economy is where diesel traditionally shined. Because diesel fuel has about 12% more energy per gallon than petrol, and because diesel cycles are more thermally efficient, a diesel engine would typically achieve 25 to 30% better fuel economy than an equivalent petrol engine. This is why over-the-road trucks are almost exclusively diesel, and why European drivers historically preferred diesel for highway driving. But, and there's always a but, modern petrol engines have closed much of this gap through direct injection, turbocharging, and other technologies. A new efficient petrol engine might achieve diesel-level fuel economy in everyday driving, removing one of diesel's traditional advantages. Finally, there's the matter of cold weather. If you've ever lived somewhere cold and owned a diesel vehicle, then you know that special joy of diesel fuel turning into something resembling candle wax overnight. Diesel has a higher cloud point and pour point than petrol, meaning it thickens and solidifies at higher temperatures. This is why diesel vehicles need block heaters in cold climates, and why you sometimes see lines at diesel stations in winter as people hope for the summer blend to arrive. Petrol, by contrast, behaves nicely in cold weather because its components are more volatile. It doesn't want to turn to wax at the slightest dip in temperature. This is one of the quietly practical reasons why petrol remains popular in colder regions. Current roles. Now that we understand how these engines work, let's talk about where they actually live in the world today. Because despite what certain internet arguments might suggest, there's actually a pretty sensible division of labor between diesel and petrol engines. It's almost like engineers, over more than a century of experimentation, figured out which tool works best for which job. Let's start with diesel, since we've been talking about it. Where does diesel reign supreme? Heavy-duty transportation is diesel's kingdom, and it will remain so for the foreseeable future. Every semi-truck you see on the highway, every train locomotive that isn't electric, every large ship crossing the ocean. These almost all run on diesel. Why? Torque. Torque is the twisting force that gets heavy things moving. Diesel engines produce massive amounts of torque at low RPMs. A modern semi-truck engine might produce 2,000 pound-feet of torque, which is enough to tow a small building, and it does it while idling around 600 RPM, barely ticking over, sipping fuel the way a reasonable person sips water after running a marathon. Petrol engines, by contrast, need to rev higher to produce their maximum torque. A high-performance petrol engine might hit peak torque at 4,000 or 5,000 RPM, which is great for zooming around in a sports car, but terrible for hauling 40 tons of freight. You can't shift an 18-speed transmission at 7,000 RPM. Well, you can, but your driver will quit. Construction equipment is almost entirely diesel for similar reasons. Excavators, bulldozers, loaders, and cranes need massive low-end power and durability to run for thousands of hours with minimal maintenance. Diesel excels at both. When you're digging a foundation for a skyscraper, the last thing you want is an engine that needs premium fuel and spark plug replacements every 500 hours. Agricultural machinery follows the same logic. Tractors, combines, and harvesters all benefit from diesel's combination of torque, durability, and fuel efficiency. Modern tractors can cost more than a luxury house, but they're expected to run for decades, with proper maintenance that is. Diesel isn't a choice here. It's practically the only sensible option. Passenger vehicles are where things get complicated. In Europe, diesel passenger cars represented around 50% of new sales as recently as 2015. The appeal was simple: better fuel economy, lower CO2 emissions per mile, and diesel's reputation for lasting forever. European countries tax diesel fuel more lightly than petrol, making it economically attractive. But then, as they say, things happened. The Volkswagen emissions scandal of 2015 revealed that numerous diesel cars were cheating on emissions tests, producing up to 40 times the legal limit of nitrogen oxides in real-world driving. This shattered public trust in diesel vehicles, practically overnight. Combined with increasingly stringent emission standards and the rise of hybrid technology, diesel passenger car sales collapsed across Europe, falling to around 15 to 20% of new car sales by the early 2020s. In the United States, diesel passenger cars never really caught on. American consumers, raised on cheap petrol and wide open spaces, preferred larger vehicles with petrol engines. Dodge Rams, Ford Escalades, not Volkswagen TDIs. The few diesel passenger cars sold in America were niche products for enthusiasts who appreciates their efficiency and torque, people willing to pay a premium and accept certain compromises. As of this recording, the future of passenger car diesel is uncertain. New emission regulations in Europe and elsewhere make it increasingly expensive to produce compliant diesel engines, and the business case for developing a new platform becomes harder to justify. Major manufacturers are quietly phasing out diesel passenger cars, with plans to discontinue most or all of them by the early 2030s. So where does petrol reign? Pretty much everywhere else. The light-duty vehicle market, cars, SUVs, pickup trucks, minivans, it's overwhelmingly petrol-powered. Petrol engines are quieter, smoother, cheaper to manufacture, and perfectly adequate for the needs of most drivers. When you rent a car at the airport, you're almost certainly getting a petrol engine, unless you specifically requested otherwise, and the rental company might not even offer that as an option. Small aircraft piston engines are almost universally petrol-powered. This might surprise you if you are expecting aviation to be more sophisticated, but the reasons are practical. Petrol engines are lighter for equivalent power, which matters enormously in aircraft. They're also simpler to maintain and operate, which is important when you're 5,000 feet above the ground and something goes wrong. Lawn equipment, motorcycles, scooters, snowmobiles, personal watercraft. Basically anything that needs a small internal combustion engine runs on petrol. The reasons are cost, weight, and noise. A small diesel engine would be prohibitively expensive and heavier than the equivalent petrol engine, and nobody wants to hear a lawnmower that sounds like a container ship. High-performance applications still favor petrol, but this is changing. Electric motors are now delivering supercar-level performance without any engine noise at all, which makes the traditional engine wars somewhat moot. A Tesla Model S Plaid will beat almost any petrol supercar in a straight line, and it does it without any combustion at all. But we'll get to the future in a moment. In fact, we'll get to the future now. We've talked about where these engines came from and where they're used today. Now let's address the question that everyone's thinking about but no one wants to ask out loud. Are diesel and petrol engines going to disappear? The short answer is sort of, gradually, in certain applications. It's complicated. Let's start with a prediction that will almost certainly be wrong. Internal combustion engines will still be around in 50 years. Probably. There will be edge cases. Specialized applications, collector vehicles, hobbyist projects, developing nations with less infrastructure, where petrol and diesel engines will continue to exist. The engine isn't dead, it's just no longer the only game in town. The passenger car market is where the most dramatic changes are happening. Governments around the world announce bans or severe restrictions on new petrol and diesel car sales within the next 10 to 20 years. The United Kingdom will ban pure petrol and diesel cars by 2030. France and Germany have similar targets around 2035. California, that regulatory trendsetter, has set 2035 as the deadline for new zero-emissions vehicles. These regulations are pushing manufacturers towards electric vehicles at a pace that would have seemed impossible just 5 years ago. Volvo, Mercedes, BMW, Audi, Volkswagen, General Motors, and Ford have all announced plans to transition to largely or entirely electric vehicles over the next decade. Some, like Volvo, aim to be fully electric by 2030. What does this mean for petrol engines? It means their end is probably in sight for passenger cars. The internal combustion engine's 130-year reign as a dominant automotive power source will likely end within the lifetime of people watching this video. That's genuinely historic. It's like watching the transition from horse to car, except this time it's the car being replaced by something else. But, and you knew there was going to be another but, heavy-duty transportation is a different story. Electrifying semi-trucks is much harder than electrifying passenger cars. Batteries are heavy, and heavy batteries reduce payload capacity, which directly impacts the economics of freight. A fully loaded semi-truck might need thousands of kilowatt hours of battery capacity to achieve practical range, and that battery would weigh tens of thousands of pounds. Hydrogen fuel cells offer an alternative, and companies like Toyota and Hyundai are investing heavily in fuel cell trucks. But hydrogen infrastructure is essentially non-existent, and the physics of hydrogen storage create their own challenges. The realistic forecast for heavy-duty transport is a gradual transition over several decades, with diesel remaining dominant for long-haul applications well into the 2040s or beyond. Trains, ships, and aircraft will follow similar trajectories, longer timelines than passenger cars, but movement towards alternatives. What about the hobbyists? What about the millions of people who love cars, work on engines, and find genuine joy in the sound and smell of internal combustion? They'll be okay, for a while at least, hopefully. Classic cars are already exempt on many emissions regulations, and there's a thriving community around preserving and restoring older vehicles. Motorsport will continue with internal combustion engines for the foreseeable future, as racing series like Formula One and NASCAR transition slowly, or not at all. The enthusiast community is small but passionate, and they'll keep these engines alive long after the automotive industry has moved on. There's also something to be said for the simple pleasure of mechanical engineering. An internal combustion engine is a beautiful piece of machinery. Pistons rising and falling, camshafts opening and closing valves, spark plugs firing in perfect sequence. There's an elegance to it that even the most sophisticated electric motor can't quite match. It's the elegance of a mechanical watch compared to a digital watch. One tells the time, the other tells time with style. So there you have it. Diesel engines and petrol engines explained in a way that hopefully made sense and maybe even entertained you along the way. We covered the origins, Otto's four-stroke cycle and diesel's compression ignition breakthrough. We explored the key differences, spark ignition versus compression ignition, compression ratios and combustion characteristics, and that glorious diesel clatter. We examined their current roles, diesel ruling heavy transport and petrol dominating passenger vehicles. And we glanced into the future, an electric transition that's happening fast for cars, but much slower for everything else. If you found this video helpful, or if you learned something new, or if you're now the most interesting person at your next dinner party, consider subscribing. We make videos about the things you always wanted to understand, but never had explained quite right. Like a friend who won't stop talking, but a friend with production value and a fairly decent audio setup. And if there's a what is question you want answered, anything at all, put it in the comments. We read them. Most of them. Some of them. A statistically significant number of them. Thanks for watching. I'll see you in the next one.